Okay, so let's get started again. So I'm going to start this afternoon by reviewing that last exercise, and then we're going to talk about, on a lecture about performance considerations. I think the schedule's got a break after that, which I think might be a little bit early. We will see what people are feeling like when we get to 3 o'clock. I might just do the managed memory lecture and stop when we get to the exercise there, and let people take a break after that. So let's get sharing again. So the exercise we looked at before the break. So what did we discuss? We discussed how you write the kernel function and how we can call it and what we need to consider when we're writing these kernels. What we need to do to execute them off. So starting, you can start from the solution from the previous exercise, or there's a fresh sort of template available to you. Either one's fine. And we're being asked to add a kernel and the execution configuration for the kernel, so you can multiply by a constant. So before we just moved data over, it had some values in it and we moved it back. This time we want to update the values and then pass them back instead. And we're going to call kernel to do this. We're going to have some kernel prototype called which is going to be in global scope, so global for the device. Called my kernel is going to take a double by value, and it's going to take a pointer to some memory on the device X. We're going to scale it on every element of the array. So initially, we're going to limit ourselves to a single block. In the main part of the program, to declare some variables of type dim3 that hold the number of blocks and the number of threads per block. And there is a predefined processor variable available to us in the program called threads per block that we can use in the first instance. Okay, that said, so here is that template. And here is our array length, and here is our threads per block. And note they are the same size initially. We have our program looks very similar. We've got constant A defined. We've got our input array, our output array, and our array device array X. Just double check if I am in the right location. Okay. So, and then we have our allocation of our device array on device with hit malloc, and then we have some copying of the values of hx, which are moved in from the host, and they've all been initialized with values depending on the length of the array, and we've copied them over into the device array that we set up. So we're going to have some call here to a kernel, and then at the bottom we've got some checking which says that whatever the output is when we copy it back, h out, doing the same pattern of moving data as we've done in our previous example, it's going to be, has to be equal to the host array times this multiplier a that we've passed to the device as well in our kernel call. So our first thing to do is to define our kernel function. Let's hit global scope. It's going to return void. Call it my kernel. And initially, it's going to take double A by value, and it's going to take a pointer to some doubles, which we're going to call result as well. Now, here is the slightly tricky bit. So I'm going to say I have an int I, and initially we said we're only going to deal with the threads with the length, the size of the number of threads in a block, which means we can limit ourselves to just going over threads. Don't worry about this whole block discussion just yet. Okay. And then we can very simply just say a result. It's going to be equal to I to A times just multiplying through by the values we've taken in and updating. Okay. But to call this, we're going to need to use our angle brackets and text down here in the clarification. So I'm at a section in the code where I know my data has been populated with hx. So I'm going to have my kernel angle brackets. And I want something inside those angle brackets, and then I'm going to pass A in, and I'm going to pass in pointed to dx, which says that's the location of data on the device to operate kernel on. But first, I need to pass in work out a couple of parameters. So I need blocks. Initially, we said we're going to restrict ourselves to one block. So we just have one, and one for each dimension. And we also need MP3, which is threads block. Now, macro value, one in the dimensions. I'm just thinking about one dimensions right now. And then in here, we just need to pass blocks and threads back in. Instead of thinking there's something needs done wrong, I think that's going to work. Now try all that. So I just did my directory. So I need to I've done something wrong. Yep, of course I have. Okay. Two things. First of all, thread index, not threads index. I wanted value. And I got this in here. Got too many S's. That's the answer to this. Let's try that again. And we submit that. We're probably going to take a moment to get running because other things will be happening. Okay. Yeah, sorry, dim3 declares struct of just 3 integers, unsigned ints. So that you've got, the idea is you can decompose in a multi-dimensional way your thread indices so that you can deal with higher dimensional problems. So if you have 2 or 3 dimensional arrays, for example, So for this example, just think about it in terms of I've just defined an int with a particular number. When we come on to look at the next example, we're going to think about a matrix which has 2 dimensions, and then we're going to think about both the x and the y values here. Okay, has that completed yet? Yes, it has. Okay. Moment of truth. Okay, so I've got my output. I've got my number of some information about the GPU, and I've got my result. I've got 256 elements, and I've got 256 of them correct. So I've done my intended kernel correctly. I've moved data from the host to the device, and I've updated it with a kernel call here. And this is pretty much the fundamental bit of calling kernels. Now we can go to more complicated things, but this is the sort of the minimal kind of example. So we're asked to do a few more things in the exercise. So I think it's useful just to go through them briefly if maybe not everyone got to them. But what if we have more than one block? So now update the kernel and the execution configuration parameters to allow more than one block. We'll keep the assumption that the array length is a whole number of blocks. Okay, so in this example, it says we're going to increase the array length, which is another preprocessor variable at the top of the file, from 256, which is currently, up to 512. So we can look at doing that. Let's go right to the top of our file. We can change this to 12, which means that the total number of blocks that we need is going to be 2, because we're going to want to give 1 bit of data to each thread. So we're going to need 2 blocks to get through the entire array. Okay, I'm not using this numBlocks parameter right now, or I can do simplicity. I want to make it a bit more explicit below. Okay, so sorry, I'm jumping around a little bit here. This is going to change how we operate on this data, because if I did this like this, I get to the end, each of my blocks, if I launch more than one now, is going to only iterate through its threads, and it's using this thread ID to do position. So they're both going to go over the beginning set of the array. So I need to add a little bit more in here to make this work properly. So the main thing I need to do here is I need the block index and the fx one, multiply this by the total size of the block, and then I'm going to add the particular thread I'm operating with. This means if I have multiple blocks, they're going to do access independent elements of the array result and update it. What I need to change then is when I call this, I now need to change how I do the execution. So the number of blocks is going to equal to array length over threads over. That should do that correctly. Now we're still guaranteeing that this is going to give us a whole number, else we're going to have issues with end of the array. If we rebuild that, the warnings, that's fine. And I would submit. You think of waiting for the queue to go through. What I should see now is that my result contains 512 elements, and this should all work out because when we defined the length of our input and outputs on the host, these were size of array length, which is 512 now because we've updated it. And additionally, our little test at the bottom, which is verifying whether we've got the correct elements, is running all the way to the array length. I'm on the CPU side, and then doing a difference and incrementing our correct value if we've done the right thing. So if we look at Slurm output from that run, which is Slurm ID 6358758. Okay, I have 512 elements and 512 of them are correct. Right, that is most of the way there. We've got one more thing we're going to do and one more thing we're going to discuss. So now we want the case where the problem size is not equal to the size of a whole number of blocks. And this is much more realistic. We'd expect to see this in our own problems. So in this case, I am going to change the array size up to 1,000. So back to the top of the file. Okay, and this means that this clearly is not divisible in terms of my number threads per block. And I'm going to have to make sure that my mathematics works out correct. I'm going to have to guard against some things as well. So now I need to make sure I do this calculation properly. I'm still going to be one dimension, but now I'm going to check that I have the following. So I'm relying on vision here. And I'm going to say my array length minus 1 over threads per block should give me the total number of blocks that fit in. And then I'm going to need one more, that's this plus 1 on the left-hand side, to do with the extra tail of the number of elements which don't fill up a whole block. And that's fine. That's everything I wanted to do. I now need to pass in one extra thing to my array, because by doing this, I'm going to have potentially run over, I'm still going to run over all the threads in that last block. And if there's not enough data there, I'm going to start trying to execute on memory that and run over the end of my array, which is bad. So I need to put some protection in. This is going to mean I'm going to change my kernel call slightly to put in some information about the size of the bound of the array I want to have. So this is, I'm going to edit the kernel call in a minute. I'm going to pass in the array length in. Turn it down. So I'm going to expect it depends when. I'm going to pass it. And now I'm going to iterate over everything, but now I need a guard. It says if you're an index I which is not greater than this length, then don't do an operation. Okay, and this should protect us against running over the end. It shouldn't impact performance because unless there's an odd number of blocks, because there will always be another block running at the same time on a different compute unit doing something else. So we shouldn't see a massive impact from doing this. And we'll look at performance next. So let's compile. My shortcuts, I'm going to make sure you see possibly progress. Right, okay. So that's going to run, and while we're waiting for that to run, I will just talk through the final little bit of this example. So what we've really done there is run our first kernel over data that's very well sized, updating and doubling a value, or we can change a to whatever else, tripling it. The example will still work. So we're doing the operation on the GPU, not on the CPU. By calling the kernel, we're dividing up the threads over the data elements in our array that need to operate, so they have independent work to do. The more independent work we can give them, the more efficient it will be. And then we've looked at increasing beyond a single block to multiple blocks. And then we started to look at problem sizes which don't fit into whole numbers of blocks. So there's a little bit of an extra exercise, which I'm not going to go into much. It would just be a question of how do you extend this to deal with a sort of a simple BLAS routine so that you then have two arrays that you're passing in opposed to one. And you're doing ax plus y. And you can simply add to the existing function with a new kernel to do that. That should follow straightforward. I'm not going to go through that just for time's sake, but you can try that yourselves if you're interested. And then the expert point here is just to say that if you don't like this angle bracket notation for launching kernels, there is a specific launcher command which you can do, which you pass the kernel as a function, and then you pass the block and threads div3 objects in as well as arguments, and that way allows you to launch in a way that may be more pleasing to you if you have a particular preference, really. But there is a mechanism for doing this in different ways. It's kind of the point. The example bottom here is just you call hip launch kernel ggl and then pass my kernel in here. Okay. I think so, yes. I can't remember testing it recently. Yeah, I thought it was. I just thanks. Right. Okay, just to go back to the example we just ran with our 1,000 elements. We now look at this. Oh, goodness, I'm wrong. So there. Okay, so we have a number of elements which do not equal the size of the block. The block size was 512 elements. And our array was 1,000, but we still got the correct answer after going over 1,000 of them. Taking a little bit longer with that example because this is kind of the core. I think part of this course, that if you understand this sort of concept of distributing your data over over the threads on the GPU and in terms of blocks, that's kind of one of the key outcomes, along with the memory management part. Those are kind of the two key considerations. Yeah, of course. We'll come on to it in the next example. But it is not, so this is not 2D, right? This is blocking in one dimension. For 2D, you'd have an extra index with an X. You can have a Y here or a Z here in this little dot X. Then you're multidimensional. At the moment, we're chunking through the array in blocks. And this is why we're going to come on to this now about performance, is the number of threads you have in a block is blocked in, is related to hardware performance. And you need to tune this for your particular application depending on how much data each thread needs to have access to. So that's starting to the cache effects start to come in. I'm going to move on now, and what we're going to do is we're going to discuss the next lecture, which is considerations for performance. And this then has a similar example, but then we're going to look at multidimensional, try and describe an array of data in a multidimensional way with this threads and blocking system. So we now should have a functioning, if relatively simple GPU program that moves some data to and from the device and executes a kernel and does operations on the device. We can now ask the question, what factors can influence the performance of such a program? So Amdahl's law states that the parallel performance of a program is limited by the fraction of code that is serial. So in the GPU context, this has two manifestations. Kernel code is potentially parallel, and host code is definitely serial, including the host-to-device transfers. Okay, so this may mean that additional work is required to expose parallelism or eliminate host operations in favor of device operations. So what you see a trend doing is trying to get your data onto the GPU and try and keep it there for as long as possible before you have to transfer it back to the host. This allows you to keep using the benefits of the GPU without paying the cost of serializing back down to the host. So the GPU has a lot of compute units, which each have many threads that can be used. Having many blocks of works available at one time is said to favor high occupancy. So this may be thought about having a very high degree of thread parallelism. However, this degree is much, much higher than you'd expect for a CPU program, where threads are usually the number of cores. And what's kind of happening here is that because the way that your blocks are set up, they are independent work, and then the GPU is able to schedule that work however it chooses over the hardware it has access to. This allows, if things get stored away from memory, it's able to switch in extra work, different work quickly, hiding any bottlenecks and getting good throughput. Okay, and this concept of GPUs are throughput machines, which high latency, because they are have a lot of work to keep feeding them. So a typical GPU kernel wants at least sort of 10 to the 5, 10 to the 6 threads to be effective. That is, the problem should have a number of have this number of elements so that you can really take advantage of the available compute units on the GPU and drive efficiency through. So if you do not have this natural sort of degree of data parallelism in your program, then you may not see as much benefit from using a GPU. That said, it may be that you need to think about how you're describing your problem to expose data parallelism in your system. Okay, so up until now, we've been discussing a one-dimensional example. And now we're going to look at a two-dimensional example, which might give us access. Sorry, the other thing I should say is that one-dimensional example was relatively small. We weren't really seeing the benefit of the GPU. We had maybe 256, then 512, maybe 1,000 threads being active at any one time. And that's not going to be a lot of work. That's not the order of magnitude we need active to get the real benefits we've just said from having high occupancy of the GPU's hardware. And you can take that, see this example here. You've got some two-dimensional loop. This is quite common. I'm going to iterate over these two indices up to 512, and I'm going to do work on each element at these locations. If we parallelize the inner loop only for the GPU, we would only work on the most 512 threads. This would be 2 blocks using the 256 threads per block value that we have been up until now. This would generate poor occupancy because we only got 2 blocks working, and we want a lot of work to be available to really utilize the many threads available on the system. Instead, if we were to parallelize both loops, then we can have 512 times 512 threads active at any one time. Divide that by 256 for the number of threads per block, and that's 1,000 blocks of work to do, which is much better. if you say there's a rough mapping between compute units and blocks to get the work done, if we've got a couple of 100 or so compute units on one of these GPUs, and we've got 1,000 blocks to be working on, then that's a good opportunity to sort of set up and get running in a stable state to really use the power of the GPU itself. Yeah, so we now have a chance to employ many compute units on this really generates high occupancy. So just to get a sense between what we call the CPU caching behavior versus GPU coalescing behavior and sort of memory usage type considerations. A given CPU in a thread in the CPU code favors consecutive memory accesses. So in C, this is the rightmost index that runs fastest in memory. So we want the inner loop will be accessing consecutive memory. This gets you favorable cache behavior and generally works towards best performance. Get contiguous accesses. Generates coalescing behavior. So for GPU global memory, it's kind of the opposite. The hardware wants to have consecutive waveforms, this kind of or blocks of work. So when you see waveforms, think about blocks of work. It's the same. It's the terminology that NVIDIA versus AMD use, and it's kind of synonymous. But you want consecutive. The hardware wants to have blocks of consecutive threads to load consecutive memory locations in a contiguous block of memory, continuous set of memory. That way, every single member of a particular compute unit is going to get the in order neighboring memory, access it, it all gets read in one line. You can operate on that one line, and then it gets passed back out. If you've not got this contiguous memory, it's going to have to do multiple reads to satisfy each compute unit for the data it wants to execute on, and that's going to slow down, and you're not going to get the benefit of the very fast, high bandwidth memory that these systems and components have. So consider the one-dimensional example. There is no issue. Consecutive threads, those with consecutive X indices, access consecutive memory locations. Okay, you're just going through an array input and passing it to array output in I. In the two-dimensional case, consider first this, where we've got I is on the leftmost index in this two-dimensional array of A output and A input. And then we're going to loop over J. So we're going to have a thread is going to access J elements each, which are going to be consecutive. So each thread gathers consecutive memory, but it's not going to coalesce the access. So multiple threads access multiple data members that are next to each other. Okay. And this is really important. If you do this, you're going to end up trying to do the same thing as the CPU, and threads get the same thread gets the next data member, opposed to the neighboring thread getting the next data member. And this is the key and the main thing around performance that can be said for these systems. So instead, what you'd want is you want something like this example where the rightmost index is getting the consecutive access, so that each of the neighboring threads gets the same gets a neighboring location in memory and can do an operation. And then when we update J, we take a whole new block, and then before we get strided memory access, and that gives us better performance. Okay, so with that said, the next exercise is to look at a two-dimensional example where you're going to implement a kernel which follows, which takes two vectors, multiplies their locations together, and then updates a matrix. where the matrix A with m rows and n columns, you have a vector x of length m and a vector y of length n and a constant alpha, and they're all of type double. So for the matrix, we're going to adopt a flattened version of this. And the reason we're doing this is because you see many examples talking about GPU programming, and they just put a two-dimensional array in here. And the point of doing this is to highlight that this is continuous. This is a single continuous access in memory, we're trying to allocate here. And we're not hiding anything in the fact that we've got a two-dimensional array. This is what's actually happening underneath the two-dimensional array. And you've got some insights. And the point is you're going to address this in this way because this is how you're going to do accessing effectively. And then you're going to try implementing this a couple of different ways. So check the template and try to implement your own version of this kernel. Try initially implementing the simplest kernel where you just have you explicitly have and do the dumb thing where a single thread does all of the work on its own and you don't take any advantage of you're basically telling all the other threads to sit idle and all the other blocks while this thread 0 is going to do all the work. And that's going to be slow. And you're going to do, through the example, do other versions of this where you're going to slowly reduce the number of loops you have, so there are no loops in the end inside the kernel execution, and that's going to give you improved performance, and depending on how you organize that access, you should see a performance difference depending on that access pattern. To facilitate timing, we've got a profiler called RockProf. If I just find the example code from in a moment, it's going to be called in. Sorry. So now, someone have a question? We have srun, it's going to call RockProf, and it's going to do a trace of the application. And in a file called rockprof.stats.csv, there's going to be a line entry for every single kernel that's called. We're going to use that. This gives a nanosecond count. This is explained in the details below on the exercise. To extract nanosecond information to compare between the different executions. One thing I might also say is that it make sure you copy your keep track of which Slurm files have got which data in it, because and the profile will overwrite your previous results. So make sure you note down the performance figures as you go, else you're going to lose track of of what you got out for the previous iteration. Okay, any questions from that? If there's no some questions, let's try this exercise for, I think we're going to need at least the next half an hour, so 3:15. We originally had a break scheduled at 3 o'clock. I'm going to go through managed memory. Change up and do that first, but I think this is an important exercise to have gone through in detail. So take the breaks when we plan to. We'll work on this for 15 minutes now. We'll take a break at 3 o'clock, and people who are interested can keep doing the exercise in the break. And when we come back, we'll discuss the output of that. So hopefully everyone's had a chance to try that exercise. What I'm going to briefly do is look at a solution for this. I'm not going to go step by step through this time simply because I'm a little bit worried I've drowned on a little bit too much. I'm going to get on to the next topics. Okay. So I share my screen. I'm just going to look at the sort of final solution and explain it a little bit here. The idea is that what you'll do is you effectively remove the innermost loop first, and then, first thing you'll do is you'll do something entirely sequential. So a single thread accesses and operates on the data, which is going to be very slow, and each of the for loops is going to run thread. So you're deliberately making something bad. So any performance improvement needs to be taken with a pinch of salt here. So you will eliminate the outer loop in I, and then just have the block run over J, and then finally remove the J loop. And the key thing here is to do is sorry, people posting timing results from the runs they were doing. And the point of this is you're adding in this multidimensionality, and this is the extra challenge with this example, is you're no longer decomposing the blocks over a single dimension. You've now got 2 dimensions to deal with. So this is kind of in the beginning of the next exercise. So if you want a slightly cleaner example of this, that's there, but there is some code here I'll just talk through briefly. So this is the kind of meant to be the optimized version. Yeah, I think the problem with people are saying that they're not seeing a massive effect from getting the coalescing right, because you're getting most of the benefit from just distributing the memory. And as long as you've got and you're doing something that's relatively simple, so I don't think that you're going to get orders of magnitude improvement from this on this particular case. Yeah. So also memcopy is dominating here. Point is to have an illustrative example that this is an important consideration, right? These are toy examples. It is something we need to think about when we come to design our kernels. And fundamentally, this is what's happening. This kernel coalescing is happening at the root level. So if you're really going for performance, and this is something you really want to think about, then making sure you're careful with this is important. So in this example, we've now got the 2 dimensions. So I remove both the loops. Okay. And the key thing is to identify the fact that J is the fastest index, and therefore it should be related to the X block of thread indices of the system, and I is moving slower, and therefore that should relate to the Y index of this block thread index structure. So the logic kind of here is that X in these thread indices, X moves fastest, then Y, and then finally Z. So it's kind of X plus, so thread index is equal to X. So I was saying this verbally is not very helpful, and I won't do it. But you can look it up. The point is you're going to start chunking over in that direction. And it means kind of you need to be careful not to fall for the trap of saying that X is related to I here. This mapping is important. Again, we're using bounds, and we'll come on to branching issues later on. But here we're testing independent threads. So having if statements is okay. If we start to do conditionals to split the work up that different threads that are next to each other are doing, then we will have problems with accessing memory in a unified way, and divergence of what particular unit is doing, compute units doing. Yeah, so this is what it looks like. I wanted to just highlight another thing is that now we've got the 2 dimensions, we need to have threads per block be 2D, and this is now set to 16. And the idea is we still have the total number of threads per block because we have 16 times 16. This is now a 2 in this threads per block parameter because we have 2 dimensions. It's still 256 in total, but now we've divided it up. And you have to change the ordering. You think about this blocks parameter here. This should be blocks Y and then blocks X because the first one is getting access to a different size than you would. So you have to change the order of the blocks and be organized here too. So that works with the array. And then you execute as you would before. Okay. So I've run this. I'm not going to make you sit and wait for the scheduler to go this time because I didn't want to make you suffer that. My results. So looking at the numbers you guys have just posted, I think I'm slightly better. So mine are running in sort of 200,000 nanoseconds, and you guys are about twice that. So I think. So maybe look at the solution in the next example. And try implementing that and see what you get out from the timing. There can definitely be variation per runs. Remember, you're on shared nodes for these executions, so they're however likely it is to be, you should be getting allocated separate CPU resource and things like that. So there are impacts that can vary these timings. This is not super clean, but the principle still holds. Okay. With that, Juan, are you ready to take over to discuss memory managed memory?
Yes. So, okay, I will share my screen. Right. This is this one.
Oh, sorry, I should say, just while you're doing that, we'll just put one other number in the chat, which is the completely unoptimized version of this, which was the serial threading, gave me as many nanoseconds just from testing yesterday. Okay, good. Okay, right. So we're getting similar results, at least a few people. So the number I posted there just now is the unoptimized version. This is incredibly slow. You're making a thread which is slower than the CPU thread, go access memory in a 1-by-1, doing multiple calls out in potentially the wrong order. So you're getting a massive speed up, but that's because you have these thousands of threads available to do work for you. Anyway, right, I'll hand over to Juan.
Thanks, James. Yeah, now let's talk about managed memory. What we have seen so far, well, now you understand that we have like two regions of memory. We have the region of memory that is in the host, and we have the region of memory that is in the device, call it the device, the GPU. And there are different ways. What we have done so far is called like, one way of calling that is explicit memory allocation and copy. So the explicit one is that, using pointers, we allocate the memory in the host with the malloc or new, depending if we use C or C++. And also we are using functions to allocate the memory on the device with the heap malloc. And also we use heap memcopy to to copy memory from the host to the device and the other way around. So this is what we have done so far. Recently, this is now there is another type of handling memory that is called unified memory or managed memory. That rather than using, rather than let's say, duplicating memory or handling the memory in the host or handling the memory on the device, now it's possible to use heap malloc managed, that the parameters are the pointer and the size of the chunk of memory that you want to allocate. And this memory will be handled behind the scenes and will be available in both the host and on the device. So here we have an example that I define a pointer of a double, and then I allocate the memory using that pointer and using the number of bytes that I want to allocate. And you see that I initialize that chunk of that array that I have allocated in the host, and then I can use that array when I call the kernel. So this array will be used on the device. So we will have, let's say, a unique pointer for both the host and the device memory. So these memories, all of these copies are handled behind the scenes. We don't need to do it in an explicit way. To release that memory, same, we use heap free. We use that function. We don't need to, this same as when we use explicit, the explicit way. So how this is handled? This is handled using the so behind the scenes, the page migration. Well, here now we are talking more about concepts that are studied or handled in operating systems. When we say a page is the smallest unit of memory management that this is handled by the operating system, and is often is 4096 bytes on a typical CPU machine. So could be the case, for instance, when we allocate the memory, and you have seen in the previous example that we have initialized the memory. This memory is initialized in the host, and then is moved to copied to the kernel, and could happen the other way around. Oh, okay, I'm trying to scroll okay, now it's moving. Here also we have a function because when the code is when this is this code is running, to give a hint to the software to say, okay, we will use this memory on the device or not. So we can this is called a prefetching. If we know in advance that the memory that we have allocate will be used on the device, we can call this function. This is called heap mem prefetch async, because it's asynchronous. So with this function, we give a hint to the software that is running, or to the software, to the how to call it, sure if this can handle by the operating system. To copy the memory from the host to the device before this is used. Otherwise, when we call the kernel will wait to until the operating system copies the memory. Here there is a note that this is implemented on Linux and is under development for Windows. But because we are using heap on ARCHER2, and ARCHER2 has a Linux OS, this is okay. So this feature is enabled to use it. There is a thing that I don't know if I have explained. Okay, here, sorry, I missed that about the memory behind the scenes is handled by the operating system. So for instance, if the GPU kernel starts and see that the memory is not available, it will issue a page fault, and the operating system will, let's say, start the copy from host to device. And to give a hint to the operating system, we can use this function. There is another way to make life easier to the memory handler of the operating system, and is using a heap mem advice. So there we use the pointer size, and also we have like 4 different types of advice, let's say. That is the first one is indicates infrequent reads. Also the preferred location of for the specified device. And also, well, the third one, we suggest that the data will be accessed by the specified device. And the fourth one is allows coherent operations between host and device. This is like a fine grain. This is like a the course of it's like a bit quite too specific, depending on the advice that we provide. So also, well, by default, each option is unset. So what since that the advice have like 4 different advices, so you can, let's say, set or unset these ones. And again, the memory is managed by heap. And when to use it and why? Well, here is recommended that, for instance, if you start coding something, you can use manage memory, and then once that you have the code, the code works, you can switch to, let's say, explicit heap malloc or heap mem copy, and check if there is an improvement in performance. What I heard, according like previous courses that I have attended regarding that I would argue that the best performance will be when you do it manually, when you do it in an explicit way. Because let's say the more that you delegate on the heap manager, or let's say the operating system, it will not know how the code will behave better than us, let's say. So if we are looking for performance, I would say that heap malloc or heap mem copy will be the. I mean, also I could be proved wrong in case that we use heap mem advice, or maybe if we use this function heap mem prefetch. I think we can also get like a good performance, but it's a thing to try and see how it goes. Okay, so now we have another exercise. We have a lot of exercises in order to try and play with the software and see what gives the best performance. But feel free to continue with the previous exercise in case that you are still testing something. But if not, go ahead and go with use this exercise. So the idea of this exercise is to use managed memory rather than explicit. So you will have let me check. It's like a replace heap malloc, heap mem copy with the function that we have learned, that is malloc manage. That is here, and test if there is any difference in the performance. Also, you can test heap mem advice. I tried to find a better definition on the documentation, but I didn't manage. I don't know why there is like an error with the AMD heap documentation that yeah, I don't get, but yeah, just play around with that, and we'll check. Let me check the schedule of today. Yeah, we can play for, let's say, 10-15 minutes, and then I will explain what shared memory is, because so far we have worked with the global memory, but the GPU has other two types of memory that we will cover today. We have a shared memory and constant memory. So yeah, as usual, any questions, please let me know in the chat, or feel free to raise your hand and unmute yourself. How is going the exercise? Are you working on it? I would like to show you, because I found on the Rockamum documentation. I will add this info. Give me a, okay, I can. Yeah, I guess that you can see the heap memory advice. These are the options that you can use. I noticed that yeah, that the first one, that is a heap mem advice set read mostly. Yeah, that's you know, the description and the name of the variable is not like doesn't match. And yeah, these are all the options that you can set or unset. Now, for instance, for the first one is that the data will mostly be read and only occasionally be written to. Also, you can set the preferred location, the device that will access that data in case that you're using different devices. Well, there the coarse grain is you can set if it's a coarse grain or fine grain. This is not covered, but yeah, later I can find more information and let you know in case that you're interested in on that. I will add this link and the information to the course material once that we finish today's lesson. I see a comment in the chat. I was typing the response, but yeah, maybe it's talking that yeah, there is a comment that is like mine seems to be slower with the prefetch. That if this is expected, could be the case also because we are playing with these codes are smaller, or let's say toy samples. Could be the case that yeah, that let's say theory and practice don't match, or maybe in this case the OS is more intelligent than us in the sense that yeah, maybe the memory is already in the device and maybe calling prefetch. That's something else. Yeah, that's also kind of, well, not kind of the issue that, but yeah, because let's say we are not controlling now, we are giving hints of how the memory is managed. I guess that in some cases it's intelligent and it works well, and in other cases maybe not. I'm curious to see, yeah, the difference, let's say the performance difference between managed and explicit memory. So since 4 p.m., what I will do is I will cover shared memory, and later you can continue with the exercise if that's okay. I mean, you can continue with this exercise, and if you have finished, you can continue with the next. and get that, yeah, we can see the have a look at the solutions tomorrow morning if that's okay. So okay, so yeah, I will explain a little bit and then leave you with yeah, like keep going with the, you can keep going with the exercises. So yeah, we have seen so far global memory. So we have some memory allocated in the host. We can allocate memory in the device, and all the memory that we are, let's say, we have allocated in on the GPU is so far is global. Also, we are using some local variables that that this is located in the stack, using some registers. And before defining what is shared memory, I would like to talk about independent accesses to global memory. So yeah, let's say the title of this part of the lesson is shared memory, but yeah, don't get confused with the, let's say that now we are still talking about global memory. So you see that we are working with a lot of threads, and each thread we're taking care that each thread accesses a given position of memory. If you notice, the threads are not like accessing, let's say two threads don't access the same position of memory. You see that the, well, okay, this here we have a, yeah, here you see my pointer. We have this example that, well, this is in like in sequential that we are going through the array and we are updating the array with a for loop. Now with the GPU, what we are doing is that. So we have a lot of threads running at the same time, and you see that each thread updates the position I in the array data. So each thread accesses an independent location in global memory, so there are no conflicts. But imagine this pattern that we have here. You see that here we have a variable called sum, and in this variable we add the value of the position I of the array data. We add it to this variable. Well, we are doing this. This is like a sequential code, a host code, so it's fine because we are doing it sequentially. There is, let's say, no conflict. But here we have a kernel that this is executing on the GPU that does you get this variable that is shared, and each thread updates that unique, well, unique, you know, this variable rather than the than before that we were only updating one position of data. So now several threads updates the same position of, sorry, position of data. I wanted to say position of memory. Now with the sum, what we have is that this variable is updated by several threads, and yeah, this is not like good, because what happens here is that when we perform this operation, we read the value of this variable, we do the arithmetic operation in the register in the, let's say, in the GPU core, or yeah, done by the thread, and then we store the results back to global memory. So if many threads are doing the same the same operation, maybe they read at different values, so it's a bit of a mess. We will get a result every time that we execute the kernel. We may get different results because this operation is not done properly, because the different threads are accessing the data at the same time. What is the solution? So that is a function that is quite well. What this is done, for instance, when you are doing this in C in sequential. I don't know if you heard about the concept of I forgot the name. How it's called? Well, I forgot the name. Is like a lock that you lock the variable, you update the variable, and then you unlock that variable. But here what we can do is, because this update is atomic, there are functions that can update the variable in an atomic way. I think also this concept, you do this in C++, you can define a variable as a atomic. But here what we have is we have a variable a function that is called atomic add. So this is the correct way to update this variable in case that we use it in a kernel. So used by by several threads at the same time. Okay, yeah, I see that this here is already mentioned about the lock. So here what you do is you obtain a log of the memory allocation, and the thing of the log is that at the moment that you access let's say you access the one thread access that variable, if other threads try to access the variable, they will wait, because this let's say the log is kind of blocking. So they wait until the log is released. So okay, let's go. Yeah, so the first step is log the variable, read the value, update the value, and release the log. And this is done for each thread. And actually, this could, for performance reasons, maybe they could like damage a little bit the performance, because there could be a lot of threads waiting to that variable to be like locked, release, etc. I see that there is a question that what is the system value for sum before a thread ready? So the thing is, yeah, exactly. So yeah, the value is in global memory, but to do the operation, you copy the value in this is like advanced concepts of memory hierarchy and operating system. It's in global memory, but to do the arithmetic operation, that value is copied in a register of a GPU core. So they perform this arithmetic operation, and then this value is copied back to the global memory. If you have any questions, exactly. So it's this is what is about the memory hierarchy, that we have the global memory, and I guess that this is copied to the cache, and then from the cache is copied to the register, and then when the register is updated, the cache is updated, and then the global memory is updated. That's why if we don't control that with the atomic operations, for maybe the other threads could read a wrong value from the cache, or a wrong value. But I'm familiar with the cache on CPUs, but yeah, GPUs, I'm need to admit that yeah, it's like still something like I'm still learning. Okay, so also note that at least yeah, any questions or something that I explained that is not clear. I know that it's like now we are like starting going a little bit advanced, but yeah, please let me know if you want me to repeat anything else, or if you need, yeah, please feel free to ask questions in the chat. Okay, just to finish the atomic addition, we can do it using integers of double precision. Yeah, this is an overloaded function depending on the yeah the values that we are adding is using one function or another. Okay, so here what we're talking about is the shared memory. Shared memory is because we are talking global memory that all threads have access, and shared memory is a small amount of memory that is only available between threads of the same block. This is a way to, because I mentioned before that imagine that we have 1,000 threads, and 1,000 threads wants to update the same value. So if we do an atomic operation, could be a lot of contention, because one thread is updating the value and the rest, that is almost 1,000, are waiting to the value to be updated, and so serialize a little bit that and damage the performance. So a way of, let's say, making different copies of this variable that we want to update is to use the shared memory, and the contention or the number of threads that are waiting will be smaller in that case. And yeah, this is mainly when we use reduction operations, that let's say that we needed the value of each thread to update like a global value, a single value. Is a way of like yeah, creating less contention. Also here we have this synchronization that because I guess that once that we finish like updating this the value that we may have in the shared memory, that remember this is like a shared within a block, we may want to copy that value that is in the shared memory in the global memory. So before doing that, we would need to synchronize the threads. So this is kind of a barrier for the threads. And once that all the threads reach that barrier, the execution continues. So we see here this like a kind of sample that you see that here we define some a temporary variable on shared memory, actually a temporary array, and we use the temporary array to we update this is to the to reverse element. Assume that we have one block. So here what we use is we use the shared memory that is like sharing the same block. Then once that we update this the value, we synchronize threads, and once that all of the threads have performed this operation, we can do the we can use this value to update my array, that my array is global. So normally this is kind of if you need to use some temporary array, you can use the shared memory that is like inside the block. And then once that all the threads are finished, you can copy from a shared memory to a global memory. Here there are some, this is important that when you call sync threads should be called by all threads of the block. If for some reason you have a condition, some of the threads will go through this barrier and some of the threads not. I mean, if the condition, let's say that is always true, fine, okay, good. All threads go through this, and but imagine that we have 8 threads, 6 of them go through this, so are waiting, and the other 2, the condition is false, let's say skip this function. So there will be 6 threads that are waiting there forever, and other 2 threads that finish the execution. So this is what is called when we work with the shared programming is a deadlock. Or shared programming, or when we work with the threads. Well, also this concept is when we use processes, but it's a deadlock. Deadlock means that some threads are waiting forever, while other threads has been finished the execution, and could be applied for processes as well. Also, this is important that when we have threads or when we write a kernel, avoid as much as possible divergence. So let's say that the if. I mean, if is we have used if in order to avoid writing something in a or writing invalid positions in memory. So you may remember at the beginning this morning we were checking, okay, if the position that I need to write is inside the array, I will write it, but in case that I'm a thread that my position, let's say my ID doesn't correspond with the array, I just finish and that's it. I don't write anything. In that case, it's okay to use a condition, because in that case you are avoiding writing in positions of memory that are not allocated to you. But in this case, that let's say, okay, if you are this number, do this operation, and if you are this other number, this other operation, that could be a little bit tricky. Could make the performance a little bit worse. Also here, here they said that you can use the work size or wave size to make things more efficient. But also that's the thing with the heap and CUDA, that they are pretty similar, but some concepts are the same, but they have different names. Also, just to finish this part, other performance concerns, that the shared memories that we have per block is not that big. Could be in the region of 64 kilobytes. So this is like an advice to when we have like a small chunk of data that we, for some reason or for performance reasons, we want to do it within the block. But you don't have as much memory as what you have on the global memory. Okay, so another exercise. So please continue with the previous one, or if you want, you can play with this one now or later today or tomorrow morning. whenever we want. Let me check. This is like to implement a Verto scalar product of the blast level 1 routine d dot. So we will need to write a kernel with this format. The idea is rather than let me check result. Result is a single scalar value. So this is a reduction operation. That reduction operation means that you get a lot of values and you calculate a value based on all of the values in global memory. So in order to avoid contention, you can use a shared temporary variable to store the contribution for each different thread in a block, and then compute the sum for the block. So in this case, rather than calling, let's say, 1,000 times atomic add, you will do it less times. And also, when you finish, you can also actually, I think you can go step by step. First, using this, using atomic add, and then do an improved version with the share, using the shared memory, and see also the performance differences between both solutions. So you need 2 versions of the kernel, so you can do that and choose. Okay, so I'll stop talking and give you some time to play with it.
So it doesn't lead to branch divergence if different compute units take different parts of the block. So you're not dividing. You have the concept of the hardware and there's a single instruction that a compute unit wants to do on all the threads it's responsible for. So if you divided it up in a sensible way, then if you block them, then it's okay. If you start doing interleaving branching, then you've got problems. They're going to go after different sections of memory, and then the instruction that all the threads are using is going to switch in and out, and then you're going to get bad performance. So that's why it's okay to do it if you do it in blocks. Obviously, there's going to be block size issues related to this, but it's safer to do it that way.
Also answering the question that is in the chat about I was talking about the divergence of like threads. What we want to avoid here is like for instance one thread. Let me I'm trying to use to show you. You see that this is like the structure. You have the grid, and the grid is divided into 4 blocks, and inside each block, let's say that there are 4 warps. So what we want to avoid here is like each warp, let's say each thread or let's say threads inside the same warp do different things. But if, for instance, the threads of one warp do something, and the threads of another warp do something else, is more. We don't break that much. That also, like in terms of memory or performance, we don't make a mess. So this is what I tried to explain before. That let's say inside the same warp, if all threads do the same, will be easier rather than doing different operations. I don't know if that makes sense or. Okay, I see that. I think it's the second question is we got Yeah, that's the idea of yeah. Thanks. Okay, I know that you're already still with exercises, but just to finish, I would like to cover the last part of the course that actually is quite short and give you a explain also the exercise and in order that you can have it and you can play with that. I don't know if you have time later today or tomorrow. Or, well, you have it for the for the future. What I wanted to explain really quick, if I manage to find the section that I wanted to explain now, is here, right? Yeah, share the screen. This will be this one. Okay, so I will explain this briefly and leave you with exercises. We have talked about the global memory. We have talked about the shared memory. That is like this shared memory is inside let's say a shared a block. So the threads that belongs to the same block can see that memory. And we have also what is called constant memory. Constant memory is when we are talking about, for instance, I don't know, an example could be the size of the matrix that we know the size and we know that it will not change. So you can have that, or maybe some constants that you want to use, or some parameters that for some reason don't change along the execution. Read-only values. So there are two ways. Normally, when you call a kernel, you send the arguments, and by definition, these arguments are in the function are read-only. Another way that you can do that is can define these values here, and you can do heap main copy to symbol and copy this you will copy these three values here in data read only. You should bear in mind that again the capacity is limited, could be like a 64 kilobytes, and in case that I don't know, okay, here we have three values, pretty small, but in case that we have like a large number of values, let's say that imagine a matrix of a large vector that is constant, you will need to use the global memory. Here is mentioned that that the large objects should not be passed value to the device. Well, this is like a more an advisor for like a C++, means that just normally when we send when we call a function, we send the values, we try to like send for instance a point. If the value is large, let's say a matrix, normally we send a pointer, because the pointer is only a memory address, and when we call the function, it's more efficient to like that the arguments of the function are smaller rather than. This is when we are working with in C. If we work with a structure, with a struct, if we want to make it more efficient, or the struct is like a way too large, to make things more performant, we set the pointer to that structure rather than structure itself. But well, this is like going a bit off topic. And the exercise now, applying everything that you have learned today, you can play or you can give a try to the matrix vector product. So there is explained, and also you could find a template on that further in section 2.06. It could be section 2.6, but well, this one. So yeah, you have a simple serial version, and you also my advice with these exercises is to go step by step. So do a change, test the change, it works, fine. So you do another iteration. So don't don't apply everything or let's say everything that you have learned at the same time. Otherwise, when you get an error, it will be more difficult to identify the line that is failing. So I mean, if it's compilation error, it's easy, but when it's a runtime error, is when, let's say, the fun starts. Again, I will stop talking. Well, we have 15 minutes, so we'll be around until 5. So feel free to continue with exercises, or you want to call it a day and enjoy. Well, here in Edinburgh, looks like it's sunny, but not sure about the rest of the UK. But yes, we'll be here anyway. I'll be here until 5. So please, any questions or anything that I can clarify, please let me know.